What I would like to recall here that we have I would like to recall that we have can you hear me? Can you hear me?
Yes, sir.
Yes, sir.
Okay, okay. We have 54 years of Caputo
Hello, can you hear
derivative,
me?
linear. This is the paper written by Caputo in 67. Also, there is another paper written by Russian scientists Zarbashian and Ersesian in 48, which includes Caputo. Also, Caputo derivative appears in this is Caputo. Caputo derivative appears in the works of Abel, Liouville, and so on. So this is the derivative, and it is an integral of a derivative actually, and the relationship between Riemann, Liouville, and Caputo. We have the right and left derivative. Also, we have discrete fractional calculus when Mittag-Leffler kernel is playing a role. This one of the papers was this Riemann-Liouville difference on discrete domain was discussed, and this is the patent I was talking is about discrete fractional map. And I kindly invite you to see this book in order to understand better about many operators, not necessarily exponential, Mittag-Leffler power law, sine, cosine, inverse trigonometric function, special functions in the kernel, so all of these integral operators. Some new papers about modification of Caputo-Fabrizio operator, it is here, and the definition of fraction derivative with the question kernel problem at the origin. So this problem was solved for Caputo-Fabrizio means for the exponential kernel was solved by Caputo and Fabrizio in 2021 in this paper, and it was applied for several equations. Another related Mittag-Leffler operators is this type of operator where we replace the kernel by Mittag-Leffler. Here we can replace the kernel, the power law kernel or the exponential kernel or by other operators, Mittag-Leffler or higher with many indices, 30 indices. We have Pratt-Hakar operator and we have multivariate functions. So we can obtain a new operators, fractional operator, with some restrictions of course, and we can apply this operator to many nice problems. This is a paper when we think about replacing the operator power or exponential with Mittag-Leffler. Paper appears in thermal science, and the integral which is the related Riemann-Wheel plus something else. Okay, so here we have Riemann-Wheel sense definition and Caputo sense. We have also the Caputo sense of this Mittag-Leffler kernel and the same integral, of course. And you can see some application, integration by parts and the application of a new non-local fraction derivative with Mittag-Leffler non-singular kernel. These are the papers in continuation of our Mittag-Leffler kernel on some new properties of fraction derivative Mittag-Leffler kernel, series representation for fractional calculus operators involving generalized Mittag-Leffler function. And these are some of our new papers related to classes of operators in fractional calculus, case study related to the physical meaning of the multivariate functions, balance equation with generalized memory, and the emerging fractional kernel. We have also a paper about final value problem from nonlinear time fraction reaction diffusion equation, discrete data, or we introduce a new operator on a fractional operator combining proportional and classical differentiation and application to hyperchaotic behaviors, optimal control and synchronization. And finally, we have one paper about. So in fractional, why we are interested in developing many operators, I am going to show in details just after this part. We like to introduce a new kernel in order to identify new hidden aspects of complex systems, which appear in modern mathematical biology, plasticity, and so on. So here is the problem of modeling. So when we have always, we said we have wrong models, but not wrong in the sense of being wrong, in the sense of being incomplete. And always we have a challenge to develop new models, to develop new operators. And these are the 5 steps model we are going to use in fractional. Ask the question, identify the modeling approach, formulate the model, solve the model, and answer the question. These are the open problems in all type of operators or fractional operators, singular or non-singular, physical and geometrical meaning, initialization of the fractional differential equation, finding new numerical method, constructing the correct version of fractional. Now we are going to show concrete examples of Mittag-Leffler function. So let us go to this idea. Here there are some papers and applications. So first of all, here in this paper, we generalize Mittag-Leffler operator, and I'll tell you briefly how it is. So this is Mittag-Leffler operator, so Mittag-Leffler kernel in the Caputo sense. Here the problem is when t goes to 0, E alpha is continuous, so the operator goes to 0. The problem is defined here in 10, the book I show you. So we have this type of problem. This condition is to some when k is different from 0, then f of a is 0. This condition leads to some unnatural restriction with the related differential equation. So our aim was to solve this problem for Mittag-Leffler kernel. For Caputo-Fabrizio exponential kernel, they solved them in a different way. Here, we would like to change this kernel, but in an intelligent way, in such a way that kernel becomes non-singular. And you see here, also the solution depends on the space of function. So now we define the new operator in this way. So you see these two operators, the old one and the new ones are related, but the kernels here are singular. So for this case, in this case, for this type of operator, we can initialize it for any values, and there is no problem when t goes to 0, but the space of function is L1. So we call this modify ABC, and we have the properties. We have, look which type of solutions we have, non-singular solution for this type of operator. So we modify the operator, we find different solutions. And for numerical point of view, we have some results, but they are not published yet, so I'm not going to present it here. But the idea is we modify the Mittag-Leffler with a different kernel, and we find different type of solution which are non-singular. So this is the problem with this Mittag-Leffler with one parameter. We have introduced the implementation of the classical ABC in a more wider space. the kernel of A and BC derivative has integrable singularity at origin. The modification of ABC leads us to some new solution of the corresponding fractional differential equation, and the fundamental role of the space can be clearly stated. Besides, the results obtained in this present manuscript show that the solution of several fractional equations with the MBC derivative, which are not solvable with the AB derivative. For instance, the homogeneous fractional differential equation with the MBC derivative and with a non-zero solution, and certainly solution without imposing extra conditions. The integral of MBC derivative is the same as the corresponding to the ABC derivative. We also report an infinite series representation for the MBC derivative. From the modeling viewpoint, new suggested modification will bring some light for both problems with the Noether singularity at origin. As a result, we will be able to characterize better the dynamics of complex system by using this modification of ABC. So for this type of operator, we have plenty. This is a series representation. We have plenty of problems to be done, including existence, uniqueness, stability, and so on, for analysis point of view, but also for modeling point of view is very important. So here in this paper, balance equation with generalized memory and the emerging fractional kernels, we consider the mechanism of a memory effect based on linear or nonlinear system of balance equation. By considering a chain of balance equation connecting each particle to the next by means of a memory kernel, it becomes possible to derive generalized expression for the overall memory kernel that connects the initial particle to the last particle. We consider several different cases and types of systems. So this is in word. Now in mathematics, the first type of balance equation is this type of system. So we have layers, and the last layer we apply a fourth layer. So the question is, what is the implication of this force on the solution of this? So we obtain here adding, trying to solve the system. We obtain P1 in this form. So obtaining the integral form the solution of P1, P2, P3, Pn. So we are obtaining in a type of rational calculus, right? Which are those? Now, depending on the kernel, depending on the system, we obtain different kernels. So, for example, power law kernel is obtained also, but we obtain other type of kernels also, including MATLAB. So this is the problem. So if you put here different types of kernels, we obtain as a solution of this system, we obtain some operators of this type. So the local memory is modified, right? So these operators have a composition rule. So for specific kernel function now, which one is give us Riemann-Wheel fractional integral? You see, integral with analytic kernel, if we have integral with analytic kernels, we can recover from this system. So this is a summation of gamma times Riemann-Wheel integrals. So we recover analytic kernel. So an analytic kernel, then we have also Mittag-Leffler function, right? Look, Mittag-Leffler function here for this type of operators appearing naturally in this balanced type of equation, right? So we have Mita-Leffler function. So Mita-Leffler function kernel appears naturally, yes. So this example shows that a combination of successive physical interaction, each modeled by a simple Mita-Leffler kernel with different parameters each time, will give rise to a generalized memory kernel in the form of multivariate Mita-Leffler function in the simple form without Pochhammer symbols, right? So three parameters are this here. So the first time we identify a system here which have has the physical meaning for kernels with one parameter emitter or with three parameters. The calculations are complicated, this I agree. So, but here we have four parameter Mita-Leffler. So Mita-Leffler kernel now can be used without any problem inside of the operator fractional because there is no problem. We give a physical meaning for the use of this operator. Concluding the paper, would like to stress on the following message addressed to our potential reader. The Markovian balance equation, initially not having memory, can serve as a possible derivation of a variety of fractional integrals and the corresponding derivative. To demonstrate this point, we consider a general scenario for the derivation of different type of kernels for fractional operators. Right. So some of them are related to Mita-Leffler kernel, one parameter, three parameters, four parameters, and multivariate parameters. So this work offers the possibility of defining a new class of fraction integral operator, which will be even more general and will include multivariate operators as well. Multivariate operators, very well known in mathematics, but now we have a physical meaning. So this is the paper that we published recently. Here, I want to do this vector simulation for Genes Caputo after I talk about Mita-Leffler kernel for three with three parameters. Let me check here. Here is only modification. I will come back to this one. And I want to show you another paper about Mita-Leffler kernel on fractional derivatives with generalized Mita-Leffler kernel. So for the time being, we discuss only the theoretical part. Here, fractional derivative with three parameter generalized Mita-Leffler kernel and their property are studied. The corresponding integral operator are obtained with the help of Laplace transform. Fraction of the presented fraction integral, the Caputo and Riemann type derivative with three parameters Mita-Leffler kernel is analyzed. So what is the problem here? These are the definition of Mita-Leffler with one, two, and three parameters, right? And using a modified version of this one, the Mita-Leffler fraction parameters is expressed in this way. So idea is the following. Idea, if you look to one parameter, if you look the E alpha beta of lambda z, it is has singularity for beta between 0 and 1 at origin. So in order to have obtained a Mita-Leffler kernel with singular, we use this formulation. And this formulation is using this definition. So we have now not one single parameter like we have in classical ABC. Now we have with 3 parameters, and this kernel is singular at origin. So when x goes to a, there is no operator a equals to 0. We have a kernel from non-singular in singular. So first we define here a and Riemann type, and we use the properties very well known with the Leffler function. Now we are going to use to find the integral. What is the integral of that operator? We have to find, and we find it with the help of Laplace transform. So we solve this equation, right? We have Laplace of ABR, right? And then we solve it with inverse Laplace transform, and we identify the integral. Actually, for a continuous function interval, that alpha is between 1 and mu bigger than 1, the left and the right fraction integrals of 2 parameters alpha and mu are defined respectively by a, b, e, alpha, mu. Is this one, so contains one part of Riemann-Liouville plus another part of Riemann-Liouville. Yes. So integral is expressed in terms of summation respect to Riemann-Liouville. Not easy, but this is the case. So these are the properties. I am not going to insist here, but what I'm trying to say that we can construct new operators, and then the question is how to use these derivative and integral operators with Mittag-Leffler kernel to obtain valuable result in modeling. So this is the problem at this moment. So we try to apply this type of operator. Let me show you here. To show you that operator, this one, to some modeling, and we apply the predictor corrector method. The paper is not published yet, that's why I'm not solve the numerical part. I will solve the predictor and corrector method for another type of derivative, but this one describes better sometimes memory effect in some complicated system. For example, from mathematical biology, where everything is possible and many open problems are there. For example, even with COVID or epidemiology, or also in viscoelasticity and viscoplasticity. Also, we can apply here instead of this kernel Prap-Hakar operator. Prap-Hakar operator, you know, invented by Prap-Hakar in 71. Very important for this all type of memory effect, and there are some work in this direction. So this is the use of Mittag-Leffler kernel with 1 index, 2 index, 3 index, many indices, and also the modification of the first ABC, because we obtain different type of solution. So we obtain solution which are discontinuous, and here we obtain different type of solutions than the other kernels. Now I would like to show you some numerical predictor corrector method for some other type of operators based on the same strategy. Define a new operator and try to find the numerical result. So on a new modification of the Erdős-Cover fractional derivative. In this paper, we introduced a new Caputo type modification of the Erdős-Cover fractional derivative. We pay attention to the fraction integral and derivative operator. There are some properties of the new modification in relationship with other Erdős-Cover fraction derivatives are derived. In addition, a numerical method is present to deal with fractional differential equations involving the proposed Caputo type Erdős-Cover fractional derivative. Okay, so what is the, Riemann-Wheel we know, Riemann-Caputo we know very well, and properties of integrals and acting on integral derivative. Erdős-Cover operator is very nice operator, it's an extension of Riemann-Wheel and has many indices and it is defined in this way, right? And this is the integral. Inverse operator is given here. Yeah. So these are the properties of the integrals of these old operators, right? And there are some modifications. Look into zero modification. This is the modification for derivative. And this is the theorem. But our problem is to find a new modification. How can you find a new modification? How can you find a predictor corrector method for this operator? So we introduce and provide some characteristics of a new Caputo type adjustment of EK fraction derivative. Initially, we investigated a visible connection between EK and the fraction integral E alpha A plus rho eta. So this is the modification, the connection, and the proof. Yes. So consequently, this EK fraction derivative, Erdős-Cover, can be reformulated in this way. Fortunately, it's a complicated formula. And we define the new Caputo type operator. So here is the novelty. We introduce the new derivative to the power n, its own Caputo type. Okay. So the question is, this is very complicated operator. Let's find a numerical solution, numerical algorithm for this. So this is a new Caputo type adjustment. And the theorem, how they are integral acting on derivative, like in Caputo. But the question is, this can be used in treating the existence, uniqueness, stability. But in application, how can you use? This is the problem. How can we use in application? We need in fractional calculus to define a numerical method how to use and how to apply and see how to compare the Caputo with this one. So this is a new operator and this is a nonlinear differential equation. So this is then transformed into integral equation, right? Where by taking the integral and then here the function f and the constant theta and rho, I assume that a unique solution of either 45 and 46 exists in the integral AB. Define an uniform B in the interval AB with n plus 1 non-equispace node. So we start slowly and this is next we will numerically calculate approximation yk for the case step of our algorithm, assuming that we have actually completed the approximation yj of kj plus 1, is that we need to provide the approximation yt plus 1 via this equation 50. Consequently, by following the derivation of the adaptive predictor corrector algorithm presented in this reference, our predictor corrector algorithm to provide a numerical approximation yk plus 1 is ytk plus 1, 45 and 46 can be derived by the following rule. So these are the rules, such that the predicted value of yk p plus 1 is yp of tk plus 1 can be found out using this formula with the weights described in 53. And g of t and y of t is this one. It is easy to note for implementation purpose that our algorithm does not depend on the choice on the values of the parameter alpha rho and eta, and so its features are similar to those of the classical Adams threshold method. Hence, our algorithm works successfully with respect to the numerical stability of the provided approximation. Now we consider Caputo type model as a test problem to solve some problems. Of course, these are academic. So this is F. You see, we have the exact solution of it. Then if you have exact solution, approximation are given in table 1. Yes, for different parameters. Here, the problem is that we have different parameters. We have to be careful. These parameters may interact with each other. Experimental point of view, we have to be careful how to apply this what type of operator. But here we have exact solution, and we have for various m, and you see the approximation is good. Now we change alpha 0.9 and t is 2. Here 0.9 t is 0.5. Not much. We didn't go out much from the one. Another illustrative example is another type of solution. We have also draw the graph here and look quite reasonable. For n is 400, the exact solution here red, predicted correlated algorithm numerical solution. So this predictor corrector method is good result. Of course, now we have to investigate more deeply this numerical solution. We need more analysis, like also for MATLAB kernels with the different indices, with one index for modified, with 3 indices, 4 indices, and multivariate. So here is the same like for MATLAB kernel, but the numerical solution was done for Ederle-Kober in the sense of Caputo derivatives. So what I would like to summarize here, I would like to summarize that there are many open problems in the area of using MATLAB kernels. One index, modified version, 3 indices, Prague-Packard, or many indices. So both are related to theoretical spending existence of fractional differential equation using it, operator also for numerical viewpoint. There are probably some problems were solved in Fractals by other authors, but many are to be developed. So we are concentrating on the predictor corrector, also for metaglacial kernel. But here there are many, many open problems and many applications for this type of kernel. And I am sure that in the future, these special functions will play, because the special function is called queen of rational calculus. Now the whole generalization of Mittag-Leffler kernel will provide a better description of complex systems, whatever complex systems will come, for example, in chaos, mathematical biology, very much viscoelasticity, optics, investigating the symmetries, solitons, according to this operator. So I think my time finished. Am I right? So thank you very much for your listening me, and I am ready to answer all of your questions.
Dear Professor, for your nice presentation, I will ask from the audience. Please feel free to ask any question related to this talk. You can unmute and ask your question from the professor directly. You are permitted to unmute yourself. Or either you can raise your hand. Dear participant, if you have any question, please unmute or you can ask. Dear Professor, there is one question in the chat box.
Yes. Can you?
Question is, explain about local and non-local kernels.
Local and non-local?
Kernels. You can see in the chat box. Yeah, you can also see in the chat box. There are some questions from the participant. Explain about local and non-local kernels.
Yes. Local kernel is, for example, class local kernels, classical derivative, classical integral that we know. Non-local kernel is a kernel of, for example, the convolution type. Let me show you here.
Hi. Morning. Good morning. Yes, I'm back.
There is a big difference, and I want to show you clearly the problem. Look here. So this is a non-local object because this depends of tau minus t, and it's a convolution type. So this is so different than our classical operator. This involves memory effect. So how can we obtain a non-local operator from a local operator? Very simple. Very simple, and I will show you here. You see the most trivial example is by taking classical integral, and repeating n times, integral of integral of integral. Due to Cauchy formula, you'll get operator of convolute type, and this is non-local because of this, right? But it's a big difference because when we work with local operators, we know we express all laws in the physical meaning that we know in mechanics, in electricity, and so on. So all started from Newton's time, Newton-Leibniz time, and all laws are expressed in terms of local operators. But these non-local ones appear in the formulation of Boltzmann in 1874. And I will show you the paper of Boltzmann when he introduced for the first time clearly the non-local operator. So this is important point of view. So introduce operators in memory. Operators in memory are of type of field-like with infinity many degrees of freedom. Local operator has only 1 degree of freedom. This is the paper when Boltzmann introduced the most general kernel non-local of convolution. Is there any other question related to this? Which are, I cannot see the chat, that's why, because I am sharing the screen. So can you tell me the second question? Hello? Can you hear me? Can you hear me?
You are audible, sir. Osman Ahmed,
Yes,
you can ask your question. Osman
okay.
Ahmed.
Hello?
Yes.
Hello, can you hear me? Can you hear me?
You are audible.
I say, what is the mechanism behind using the canal?
You are audible, please.
What is the mechanism behind using the canal?
Mechanism
behind using the kernels.
Yeah. So why did you use the kernels? Here in this paper, 1874. So he would like to find the most general kernel operator in the sense of integral